The Fermi paradox asks the question, if aliens are out there, where are they? Maybe they're already here and are watching us right now, and we wouldn't even know because their technology is vastly superior to ours. Maybe there's nobody intelligent out there in the first place. Maybe they're hostile and we'd better keep quiet. Or maybe the most logical answer is we've only just begun exploring space and sending our signals out there, and maybe not enough time has passed for anybody to notice us yet. After all, our radio signals rippling out into space haven't gotten much further than just over 100 light years. And as a matter of fact, these random waves of all sorts of local broadcasts are too weak to stand out against the background noise of space. So even if they pass by a planet with an intelligent species, they will most likely not be able to detect them. We've also only just taken our first interstellar baby steps when the Voyager 1 probe left the solar system in 2012, which is by all accounts not very long ago. The two Voyagers and Pioneers are all set on course for interstellar space in different directions, but they're all roughly the size of a van or somewhat smaller. And once they run out of power, they definitely won't stand out against the cold depths of deep space. The saying, looking for a needle in a haystack, doesn't quite get across how unfindable these machines truly are. So even if the galaxy is teeming with advanced alien civilizations, the odds some or even one of them would bump into one of these old dead machines are quite literally astronomically small. Now that they're out there is by all means an incredible feat of science and engineering, but all in all these machines are very slow and they're not going anywhere in the foreseeable future. None of these probes are headed for any particular star, but will eventually fly past a few. Pioneer 10 is going in the general direction of the star Aldebaran, currently about 68 light-years away. If the star had zero relative velocity, meaning its position relative to our system wouldn't change over time, because everything's rotating around the center of the galaxy, it would take the probe more than 2 million years to get there. Pioneer 11 is headed towards the constellation Scutum and will pass near the dwarf star TYC 9921921 in about 930,000 years. In 4 million years, it will fly by the star Lambda Aculi, a yellow star 3 times as massive as the Sun. Voyager 1 will pass within 1.7 light-years of the red dwarf star Gliese 445 in about 40,000 years. Voyager 2 will pass by the small star Ross 248 in about 42,000 years. If left undisturbed, it will continue on and pass the star Sirius, the brightest star in the night sky, in 296,000 years. Just to drive the point home, in an older video I've made, I tried to convey the size of the solar system by showing how long it would take to walk to the planets, if you kept a steady pace of about 5 km per hour. Walking to the moon would take you 9 years, walking to the sun would take 2,123 years, and walking to Pluto 1.3 million years. Now with modern rocket technology, we can go to the moon in just a few days, no big deal, but New Horizons took 9 years to reach Pluto, even at the incredible speed it was going. Now that entire video is about how incomprehensibly big the universe is, and it's a subject that I find truly fascinating, but also a bit depressing at the same time. The general pop science idea is that, sure, alien life seems to be pretty much a given. There are billions of galaxies filled with billions of stars, and the overwhelming majority of them have planets. In our own galaxy, we found thousands of exoplanets in just a few decades, and our technology for finding them has vastly improved. So far, we haven't found exoplanets with readings that seem to be caused by alien life, but it seems like it's just a matter of time, and alien life would for sure be a good reason to pay an exoplanet a visit at some point in the future, once we figure out faster ways to travel space. Well, the rare Earth hypothesis poses that in order for life to develop, it requires very specific and maybe even unique circumstances. But really, we don't even know how life began here on planet Earth, so it's hard to say for sure. Life needs this or that to happen, but we can make a couple of educated guesses. Like smaller, cooler, sun-like stars seem better for life. Liquid water is probably important, right distance from the parent star, so it's not too hot or too cold, and preferably a smaller rocky planet similar to our own. If we did find it, hard evidence that some exoplanet is teeming with life, or maybe we will find hard evidence that microscopic life once existed on Mars, or exists right now on another planet or moon in the solar system, that would for sure be the biggest discovery of our lifetimes. Easily one of the biggest in all of human history. Science fiction stories often say, what if we found another complex, intelligent species? But that's by far not the only kind of life we could find out there. And if we go by what we find here on Earth, there's been exactly one species in the 4 billion years of history of life here that's been capable of space exploration in any kind of way, by inventing instruments like telescopes to study the universe with, and by physically leaving the planet. Just one. Even complex multicellular life is in a minority on Earth. Most living beings we can find here are bacteria, microscopic, single-celled organisms that just eat, replicate, and die. And that's all they've ever done for billions of years, and most likely will be doing well into the distant future. They're the most successful life form we know of. They're the first living beings we know to ever exist on Earth, and might be the last as well, until the sun burns out and turns the Earth into a charred dead rock, if it survives the death of our star in the first place. This is also a part of the rare Earth hypothesis that basically life may be very common in the universe, but complex life, intelligent life like ourselves, may be extremely uncommon, or even unique. So if we do find alien life one day, it would seem quite likely that it will just be a planet full of bacteria-like beings. Which would be incredible, but not quite like life on Earth like we know it. I say all of this because sometimes I feel like when or if we someday confirm alien life beyond a doubt, people may be disappointed when it's not Vulcans or something. No crazy technologies like faster than light travel or Dyson spheres, but simply bugs. And then it would be a major challenge to study those alien life forms very closely, considering the distances between the stars. Even in the dense galactic cores, stars are on average still 160 billion kilometers away from each other. Scale down to more intuitive distances, that comes down to a ping pong ball every 3.2 kilometers. The closest star to the Sun, the small red dwarf star Proxima Centauri, is about 4 light-years away. If the Sun was a ping pong ball, Proxima Centauri would be a p 1,100 kilometers away. Proxima Centauri does have planets, and one of them is roughly Earth-sized and in the star's habitable zone, so may potentially host life. There currently are concepts for long-distance space travel technology to Alpha Centauri's system. One way would be using nuclear pulse propulsion, and yes, that means the spacecraft's thrust would come from nuclear explosions, small ones of course, and that could get a probe to the system in about a century. That's still quite long though. Project Breakthrough Starshot investigates the possibility of a fleet of light-sail interstellar probes that would be propelled by lasers. The fleet would consist of about 1,000 small, lightweight spaceships and ideally could reach the Proxima system in just 20 to 30 years. Now, as it is, this project comes with a lot of challenges. Light propulsion requires a huge amount of energy, extremely powerful lasers to shine at these light sails to propel the spaceships with. And so these spaceships would have to be very, very small and lightweight, just a few grams, and then you have to fit a power source and the light sail itself and a computer and a power source into a tiny, tiny spaceship like that. Current technology is not quite there yet, that we could make a space probe of just a centimeter at most in size that can fit all the instruments it needs to then fire lasers at it worth 1,000 gigawatts of power to speed them up to between 15 to 20% light speed. And then you have to make sure your fleet of teeny tiny lightweight spacecraft can survive the extreme acceleration, the cold vacuum of interstellar space, and collisions with space dust for many years. Now, it's an incredibly amazing concept, but you can imagine it's going to get very complicated and not to mention very expensive to pull this off in the near future. Now, maybe it will happen in our lifetimes, who knows, and we'll have probes flying to Proxima Centauri and taking close-up pictures of an exoplanet in, I don't know, the next 50 or 60 years. After all, landing people on the moon seemed like an insane thing to do in the first half of the 20th century, but then we went and did that. And then we sent probes to the furthest places in the solar system and beyond. Now, 20 years to travel 4 light years is still kind of slow, all things considered. At that speed, you could get to the star Sirius in about 40 years, which is still a lot faster than the 290,000 years it's going to take Voyager 2 to get there. But okay, 40 years, this is still pretty doable, and this way we could realistically visit all the nearest star to the solar system within reasonable timeframes. The technology we would need for Project Breakthrough Starshot does exist, it just needs to get smaller and then we're good to go. It's really not that crazy if you consider that just a few decades ago you had like a separate radio and record player and a video camera and a phone and all of that and a computer, and now it's just this. You can do all of those things with your phone. So yeah, that looks like we could visit all the stars in 10 light years distance, investigate any exoplanets they have for life in the next century, give or take, maybe in the next 2 centuries. It's hard to imagine what the future will look like. Obviously, technology will vastly improve. And so will our methods for space travel and detecting exoplanets and potential life there. Currently, there's over 5,000 known exoplanets and more are being discovered all the time. Okay, I'm gonna take a little detour here and talk a bit about exoplanet detection techniques because I think this is just really cool to talk about. Scientists today have several methods to find exoplanets. They can detect if a star wobbles as the gravity of an orbiting planet tugs at it, and it wouldn't wobble if it didn't have any planets. The wobble shows up as a difference in frequency of the light coming from that star. As the planet tugs, the star kind of leans away from us a little bit and then leans back towards us again a little bit, and so its light will go from being a little more redshifted to being a little bit more blue shifted than if it didn't have any planets. This is called the Doppler effect and applies to all sorts of waves, and is the same effect as the change in pitch of an ambulance siren as it rushes past you. You can clearly hear the pitch goes from higher to lower. Now, if we look at a star from above instead of sideways, another wobble measuring method is used. Astrometry measures tiny changes in the star's position as the planet's gravity tugs at it. You do need very precise data for this method, and so far only a handful of exoplanets have been found this way. Scientists can also measure the amount of light coming from a star to see if it dims slightly in regular intervals, which means that a planet is orbiting it and blocking out light as it moves in front of the star, from our point of view. Basically an eclipse from very, very, very far away. Now this method only works if the orbital plane of an exoplanet is between us, the observers, and the star in question. Some exoplanets have been observed directly, but this isn't the best way to find them, since especially smaller planets get completely outshined by the glare of their parent star. All in all, pretty amazing and clever ways to find planets that are the size of the Earth, and sometimes even smaller, around stars that are thousands of light years away. The next big step is actually finding signs of life on a nearby exoplanet. We'll need extremely sensitive instruments, like space telescopes. The best space telescope we have right now is the James Webb Space Telescope. It's capable of capturing low-energy light from deep in time and space, from when the first galaxies were still forming. But it can also help us study exoplanets, and in particular the chemical composition of such a planet's atmosphere. It can even help with finding oceans on exoplanets. Until we actually find alien life, our ideas of where to find it could potentially be extremely broad. Earth-like planets for sure, but why not any terrestrial planet? Oceans under a thick layer of ice, like Jupiter's moon Europa. Or lakes of liquid methane like on Saturn's moon Titan. Who knows, even the volatile outer atmospheres of gas giants. The possibilities seem nearly endless. It would seem more likely, however, the search for life needs to be narrowed down to only planets that are similar to Earth, orbiting at a distance of its parent star that liquid water can persist on the surface, and a whole list of characteristics including size, the composition of the atmosphere, geological activity, the influence of moons, the influence of other planets in the system, a smaller sun-like star that isn't too energetic because stellar flares can destroy budding life forms. But not enough activity might not get the right chemistry going either, and even the place in the galaxy of the system could matter. Either way, there's a good number of exoplanets relatively nearby that seem suited for life. Now, we've only just begun investigating exoplanets. Do keep in mind many of them are Jupiter-like gas giants that sometimes orbit their star very closely. And not all of them orbit smaller stars like red dwarfs or sun-like stars. I mean, the first ever exoplanet discovered orbits a neutron star. So yeah, who knows if life could exist there? Still, scientists like to focus on Earth-like planets in the habitable zone because the life on Earth is the only example we have so far. So maybe we wouldn't even recognize life forms that are too different from us. Ideally, we find life on worlds in our own solar system, which make it a lot easier to study, and potentially find out more about how it got there, and what kinds of environments we can keep in mind in our search for life on exoplanets. If life can happen in the methane lakes of Titan, then we can broaden the search to extremely cold worlds. If life can happen in the atmospheres of gas giants, we can investigate those as well. But it has to be said that seems highly unlikely, since the atmospheres of gas giants are incredibly volatile places. Molecules get blown around and up and down constantly, and you probably do need a fairly stable environment for complex chemistry to take place. So if we can create our fleet of tiny spaceships that can go 20% of light speed, we could visit Proxima Centauri b, the closest Earth-like exoplanet. Unfortunately, as it is, it doesn't seem this planet is a good place for life to happen. It's tidally locked, meaning one side always faces its sun, like how our moon always has the same side towards Earth. So one side of the planet is always hot, and the other side always cold, and you only have this narrow band of moderate temperatures in this twilight zone. Also, while being a small red dwarf, Proxima Centauri itself is quite a lot more active than our own star. And all this radiation may have just blasted any life off of the planet's surface. Now, there could still be some under the surface, or tucked away in places radiation can't reach. Pretty much impossible to detect from a distance, however. We're still wondering if small colonies of bacteria could exist deep underground on Mars, but you'd have to build and send an incredibly advanced robot to find them. Or humans, but a robot would still be easier. So you can imagine how complicated finding alien bacteria on a planet 4 light years away could get. The next closest Earth-like world is in the Gliese 667 system, a triple star system only 22 light years away. The planet Gliese 667 CUC, so the third planet from the third star in the system, is only slightly warmer than the Earth itself, but it orbits quite close to its star in just 28 days, and so it may be tidally locked as well, which doesn't do habitability any favors. Other relatively nearby Earth-like planets include Kepler 186f, being just a little bigger than Earth, and with an orbit time of 130 days, it seems like a great candidate for habitability. But it's 580 light years away and too far for existing telescopes to analyze its atmosphere. Kepler 62f is currently one of the most promising candidates for a truly Earth-like exoplanet, similar in size, and orbits its relatively calm star in 267 days. But it's also 980 light years away. Kepler 442b is another planet that seems very Earth-like, orbiting a smaller star some 1200 light years away. A little closer to home at 300 light years, Kepler 1649c is a rocky planet slightly bigger than Earth, and its host star doesn't seem to flare up very often, which is all good news, but so far that's pretty much all we know for sure about this place. And in case you're wondering, all these planets are called Kepler because they were discovered using data from the Webb Space Telescope. But at only 40 light years, we have the TRAPPIST-1 system, with a whopping 7 rocky planets between roughly the size of Mars to just a little bigger than Earth, orbiting a cool red dwarf star, and 3 or 4 of these planets seem like great places to harbor alien life. And because the system is so close to us, it's within the Webb telescope's range to gather good data on atmospheres of the planets. Now, so far, 2 of the potentially habitable worlds, B and C, show no signs of a proper atmosphere, and they have extremely hot dayside temperatures. So that's a bit of a bummer. Now, what if, let's just imagine, we found signs of life on one of these planets just 40 light years away? With Project Starshot Breakthrough, it would still take 200 years, give or take, to go there. So then it seems to be a matter of improving technology so we can go even faster. Keeping in mind, going faster does require more energy. You can never actually reach light speed because that would take an infinite amount of energy. Also, it will take a bit of time to accelerate any spaceship to that speed, because if you could somehow invent a spaceship that could get to light speed or close to it instantly, you would destroy it. The faster you go, the more you have to take into account relativity issues. I'm talking about time dilation, one of the more bizarre consequences of the theory of relativity. If you go faster, approaching light speed, time passes slower for the people you leave behind at normal speed. Your watch will count the seconds just fine, and so will all the watches of people at home. Time would pass normally for everyone involved, from their perspective, but if you went at 50% light speed, less time will pass for you than for people at home. If we could somehow build a spaceship, we could accelerate to 99.5% of light speed for a trip to Proxima Centauri in about 5 years. Taking into account acceleration time, the computer of that ship would count 5 years. Any passengers would age 5 years, but everybody on Earth would age 50 years. They would also have to wait 50 years to hear back from that super fast spaceship. It's so strange because going faster doesn't really make you faster, at least not in a way that matters for deep space exploration in a reasonable amount of time for everyone involved. Even to the nearest star to the sun, and that distance is comically small on the cosmic scale. Now, the time difference wouldn't be that significant at 20% light speed, which seems to be the most feasible speed we could reach in the foreseeable future. But like I said, that speed isn't taking us anywhere truly far. Now, if we did find an alien civilization in the TRAPPIST-1 system at 40 light years away, we couldn't visit them for hundreds of years. In fact, even communicating with them would take a stupid amount of time. Now, nothing can go faster than the speed of light. No wave or particle goes faster than that. And so it would take 40 years for any message we can send to reach TRAPPIST-1. And then we would have to wait another 40 years to hear back from them. So we're looking at about the average human lifespan just to start a conversation. It would be a work of generations. Your parents could be on a team responsible for sending a message to TRAPPIST-1, let's say on your first birthday, when they are 30 years old. You will be 41 when that message arrives there, and your parents will already be 70. If the people of TRAPPIST-1 can send a message back on the day they see it, you will be 81 years old when it gets to Earth, but your parents won't live to see that. If you have a child around the same age your parents had you, they will be in their early 50s when the return message is sent to TRAPPIST-1, which will arrive when you are long gone. If you have any grandchildren, they will be in their 60s and your own child in their 90s with any luck. So the next response coming from TRAPPIST-1 will arrive for your great-grandchildren when they are 70 years old. We're already looking at 160 years into the future. If we consider how much society has changed in the past 160 years, I find it hard to imagine anyone keeping up with a conversation with TRAPPIST-1 for that long. One solution would be to use computers and artificial intelligence. After all, a machine doesn't get tired or bored. It can be fixed and upgraded as long as someone or another machine keeps up with maintaining it. Machines, computers, and robots have been doing the majority of space exploration since the very beginning. It's simply much easier to send a robot to another planet or into deep space. A machine can hibernate until it arrives to its destination, even if that takes years. The New Horizons probe slept for the 9 years it took to reach Pluto to save power. Okay, so we've decided to go to TRAPPIST-1. With Project Breakthrough Starshot, that's still going to take 200 years. Maybe less if we can build faster probes. But not too fast or we'll have to wait even longer, though the problems with time dilation don't really kick in before you get to like 80-90% light speed, but you still need a lot of energy to get to that speed. But anyway, the people that start that mission probably won't live to see it, but we can program machines to keep track of it. We can wonder if machines will be our ultimate tool for deep space exploration. Nobody can predict the future with 100% certainty, but humans aren't made for space. Not only would we die extremely quickly, and horribly I might add, when exposed to the cold and unforgiving depths, we also just don't live long enough to cross the vast empty distances between stars. Keeping a crew in hibernation for a long time isn't something we're anywhere close to being able to do. Even if we could do it, it really would be so much easier and cheaper to have machines do it for us. Who knows, some of our descendants will one day wake up to the news that a deep space probe has reached the TRAPPIST-1 system, and this was at long last confirmed by a message the probe sent back to us when it arrived, 40 years before. The machine would have to operate completely autonomously, since 40 years is way too long of a time to send it new directions. So it would need a highly sophisticated AI to work on its own, and instruments and a power source that can last in space for a few centuries at least. Considering how quickly technology develops, these issues will likely get resolved given time. And then we would have sent machines to a couple of the nearest star systems in timeframes that are hard for us right now to really imagine. But again, it's hard to predict the future. Maybe we'll find a way to slow or even completely stop ourselves from aging. Maybe we'll find a way to upload our consciousness into robotic bodies that don't break down. And so we could at long last embark on deep space exploration missions ourselves. Many sci-fi stories show us an alien species explore the universe in person. It's the ultimate dream. But wouldn't it be easier and cheaper for them to send machines? The amount of time it takes to travel a few hundred or a few thousand light years won't really matter if your spacecraft is advanced enough. The first visitors to our planet might as well be robots, carrying precious knowledge of a faraway civilization, kind of like how the golden records on the Voyager spacecraft now carry information of our society into deep space. If someday, somehow, an alien civilization found one of the Voyager spacecraft and figured out how to access the information engraved on the record, they would see a snapshot of our planet and our society at the time the record was made. Our spacecraft might as well end up on the other side of the galaxy 1,000,000 years from now. They would find an ancient relic of a people and a planet that will be drastically different so far into the future. Humanity may still be around, there's no way to tell. Would they find it interesting or useful at all to come find out what happened to the people on the record? After all, the farther a probe travels, the longer it will take to communicate back and forth. Even if you can make a power source that can last 1,000,000 years, even a highly advanced intelligent probe at some point will fly out of practical reach of its origins. If you send a machine to a planet even just 1,000 light years away, it'll take that long for any message to come back. What would be the state of the world it will come back to? Will anybody still be listening back home? Now maybe you're thinking, surely an advanced enough species will find a way to circumvent this speed limit of the universe. Make use of the loopholes there seem to be in the theories of relativity. Sure, physics as we know it today tells us there really doesn't seem to be a way to go faster than the speed of light, and Einstein's theories have withstood many tests and hold up just fine even after so many years. But there are hypothetical ways to go fast without breaking the speed limit locally in your little pocket of space by bending space-time itself. A wormhole is such a solution, a point where space is warped in such a way that two distant points, millions or billions of light years away from each other, are connected. Go through the wormhole and you can arrive at the other side of the galaxy almost instantly. Another idea is that you could build a special machine that generates a field of energy that's so strong it can expand and contract space itself in such a way you create a bubble where your ship sits in, but this wave in space-time allows you to travel great distances faster than light, without violating the speed limit. This exotic way of traveling space was first conceived by Miguel Alcubierre in 1994, and so it's called the Alcubierre drive. Unfortunately, both of these solutions come with a whole lot of problems. First of all, so far there is no evidence that suggests that wormholes exist at all. Sometimes people believe the immense gravitational wells of black holes sort of puncture a hole in space that has a so-called white hole on the other end. And this other end may even be in a different universe. It's an incredible idea, but really the gravity of a black hole is so immense that anything would get ripped apart if it fell into the hole. No matter what there actually is beyond the hole's event horizon, the point of no return, from which nothing can come back. Not exactly the most practical way to travel. Even if you could go past the event horizon and not get torn apart, you still couldn't come back and tell the tale. The speed at which you would need to travel to escape the black hole past the event horizon would be faster than the speed of light, and that doesn't seem possible. Space past the event horizon is bent so strongly by gravity that you'd always be going down, no matter what direction you would be going in. Bizarre, I know. Because of this, no information can escape, so functionally we have no clue what goes on in there. A singularity, a wormhole, a type of exotic stellar remnant, or whatever else, there's no way to find out. There's also a good number of problems with the Alcubierre drive. It would require negative energy, something that may or may not exist, and might rely on harnessing dark energy somehow, which we also don't know much about, except that it seems to be responsible for the accelerating rate at which the universe is expanding. At the very least, you can say it's just not practical to build such a thing. In its initial concept, in order to work, the drive needed an amount of energy greater than the total mass of the observable universe. Later, this was adjusted to about 3 solar masses, but 3 suns worth of energy is still quite insane to generate, let alone handle practically. The drive shell material would have to be extremely thin, approaching the Planck length, the smallest measurement in the universe. So even if we could somehow figure out a solution for the energy requirement, the Alcubierre drive faces incredible technical challenges. Even if it can work on paper and not break the laws of physics, how do you build it? How do you build a machine with walls so thin you literally can't make them any thinner? Also, you would have to warp space and create this bubble before you can put anything in the bubble, so again, how would that work? Basically, your warp drive would have to exist already before you can build one in the first place. Either way, any type of faster-than-light travel messes with causality, and that also seems to be entirely impossible. Causality posits that all of reality is driven by an unbroken chain of causes that lead to effects, which in turn then become causes for new effects and so on and so forth. You exist because your grandparents got together, and they exist because their parents got together. And you can trace this line back all the way to the first life forms that ever existed here. The Earth exists because the Sun exists, and the Sun exists because about 5 billion years ago, a cloud of gas and dust began to collapse under its own gravity. That cloud of dust existed because other stars were born and died before, and all of the atoms in the universe that make up clouds of dust, stars, planets, and you and me and everyone exist because the Big Bang happened. The event that was literally the beginning of all of space and time that we know of. The fact you're watching this video right now is a consequence of the Big Bang. We're living inside remnants of a higher dimensional explosion. Causality, therefore, seems to forbid time travel. The classic example of why going back in time in particular causes all sorts of trouble is the grandparent paradox. If you could somehow travel back in time and murder one of your grandparents before you were born, you would prevent yourself from existing. And so you also would not exist to travel back in time to prevent yourself from existing. Going faster than light would technically allow traveling back into the past, sure, but causality tells us things can't happen before they have happened. You can't travel faster than the speed of existence itself. Photons travel at exactly the speed of light, but you wouldn't expect to see anything before a photon reaches you, and so any information photons carry cannot be understood before they reach an observer. Traveling faster than the speed of existence is just something that doesn't seem to work. How could you, with the unique atoms and chemistry that make you right now, go to a point in existence where there's no cause for you to exist yet? Relativity tells us very fast things can travel into the future, but only compared to those left behind at normal speed. This very fast traveler wouldn't age any differently in their frame of reference. They wouldn't happen any differently, in other words. Time would still pass for them normally. They'd still experience cause and effect. And growing older will still get you wrinkles and gray hairs, even if you will age much slower from the perspective of the people you left behind on your very fast journey. The closer you approach light speed, the greater time dilation is. Going at 99.5% light speed for 5 years means 50 years will pass for the people left behind on Earth. Now, for anything traveling at exactly the speed of light, no time will seem to be passing. For you, it would seem like you arrive at your destination instantly, like you're teleporting there. But for an outside observer, you would still take exactly 4.24 years to reach Proxima Centauri. In order to travel faster than light, you would have to travel faster than instantly. In other words, you would have to arrive before you've even left. You can't go faster than time itself. You can't exist in a point in time in space. There's no reason for you to exist yet. There is no effect before a cause. Even clever space-bending tricks that work on paper, like wormholes and the Alcubierre drive, potentially violate causality, and so they're most likely not possible, or at the very least highly improbable and impractical. Of course, scientists don't know everything, and they will readily admit that. Our current understanding of physics can change with new discoveries and new information, and there's absolutely no reason to say that we've figured it all out by now. In fact, there are still plenty of things we know we don't know, and then even more things we don't know we don't know. I hope that makes sense. But for now, certain things like the speed of light and causality do very much appear to be the hard limits of the universe that can't be bent or broken. And so to go back to deep space travel and the Fermi paradox, perhaps the solution is that there really is no way to do deep space exploration in a practical way, and we're all stuck in our own stellar neighborhoods. I think sometimes people mistake science to be this thing that we do to make anything we can dream of possible as long as we try hard enough. But really, science is a method for us to understand existence by making observations and conducting experiments. If the information we win by doing this tells us certain things are impossible, then it's not up to us to deny reality. I've had people comment on videos that I lack imagination because I sometimes talk about things being impossible, but that's not the point of science at all. Scientists have imagined time travel and wormholes, but they unfortunately found that these things don't actually work the way we would like them to. Keeping all this in mind, deep space exploration comes with a lot of serious challenges, limitations, and caveats. It's not impossible, but we're all bound to the rules of our universe, and so is every alien civilization that might be out there. The speed of light is sadly a snail's pace compared to the size of the universe. Maybe the solution is that any advanced alien species simply decides that deep space travel isn't worth it. Suppose today some alien civilization 10,000 light years away finds our planet and can detect life exists here. Now they are looking at our planet as it was 10,000 years into the past. That long ago, our ancestors were still figuring out agriculture and a good chunk of them were still hunter-gatherers. Most likely, those aliens can't predict the future either, so they might just catalog Earth as a planet with lots of life, albeit primitive, and continue searching for a planet with readings that show a technologically advanced species lives there. If those aliens would look at us again 10,000 years later, they would perhaps detect the armada of satellites orbiting our planet, and they'd be happy to have found a techno-signature, a sign an advanced civilization lives there. The question then is, would they find it interesting or useful at all to send a space probe to us? It will be on its way for much longer than 10,000 years if they go anywhere below light speed to avoid the problems with time dilation. And any kind of communication back and forth with this probe will take 20,000 years, and any information about themselves they send with this probe would be horribly outdated by the time it gets here. Also, what would our civilization look like by that point? Will we even still exist? Will we have left behind anything to discover? Maybe a machine that can tell this alien visitor all about the fleshy, short-lived beings that designed and built it so long ago. Would future scientists here on Earth find it useful to send a machine to a distant exoplanet to investigate it, knowing how much society can change in a few thousand, even a few hundred years? Deep space exploration is a huge challenge because it takes such a long time. Longer than any of us will live for, potentially longer than our species has existed for. If intelligent and advanced species are indeed uncommon, how will they find each other among the trillions of planets orbiting millions of stars? Will they even exist in overlapping time frames, or will they find nothing but remnants of people that are long gone? Will there just be machines coursing through the emptiness, searching for signs of life that got snuffed out eons ago, carrying ancient knowledge of civilizations that might not even remember them, while the stars die out and the light in the universe fades? And that's just in our own galaxy. Our closest galactic neighbor, the Andromeda Galaxy, containing 1 billion stars and currently sitting 2.5 million light-years away from us, will merge with our Milky Way in 4.5 billion years and make one big galaxy. But most other galaxies outside of the local group are moving away from us. The universe continues to expand, and it seems it will keep doing so indefinitely. Right now, we can still see and study other galaxies and clusters, but in the distant future, no other galaxies will be visible from our own. And if anybody is out there, they won't see any others either. And so we're all getting lost. Not only to space, but to time as well. There are no guarantees for the future. We, or somebody else out there, might find a way to travel the universe quickly without breaking causality. There may be intergalactic societies one day, or not. In a way, it is frustrating that a human lifetime is so short in the grand scheme of things. Sure, being alive today comes with the perk of already having so much knowledge available, and surely we can dream of all kinds of futures, but we will never know. All we can really do is our best with what we're given. Thank you for spending some of your limited time with me. If you have any questions or any remarks, that's what the comment section is for. I hope you learned something new today, and I will see you in the next video.